So let's now apply the frequency response to an example. So let's say that we have an example transfer function here, g of s, and let's let g of s be equal to 1 over s plus 1. Really simple equation, and we want to see how when we put our frequency, when Valerie sings into our system some frequency, what does it look like on the outside? And the response will depend on the frequency that we're putting into it. Okay, so I've rewritten over here how we can go from the frequency response, sorry, not the frequency response, the transfer function here to the frequency response itself. So the magnitude and the phase shift that it will cause. Okay, so here's our input function. So we now need to take our g of s and put in s equals j omega to see how this system will react. So we're going to put j omega here plus 1. So this is what we're going to be testing. But the question is, well, what value of omega do we choose? This is 2 pi frequency, right? And we want to try a bunch of different frequencies. So we'd start at a low frequency maybe and increase to a higher frequency and see what we get as an output. So what we're going to do is we're only going to test a few points, but we're then going to draw it on the S-plane so you can see how this system will change as we change our frequency. Okay, so let's first take a frequency. So we're going to start with actually 0. So if we so S equals J, we're going to say 0, we need to look and see what the magnitude will be. So we're going to make a little table here, mg, so the magnitude, and then the phase of our transfer function. Okay, so let's take this and put this into our magnitude first. So first we're going to put 0 into here and look at the magnitude of it. Okay, so we would get 1 over, and we have 0, right? So 0 plus 1, well, that's just 1. We want to look at the magnitude of that, right? So that's 1. Okay, and then we would do the same thing, but then look at the phase of it. So we take the same thing, look at the phase, angle, same thing. The angle of 0 plus 1, which is just going to be 1, right? The angle of 1 on the S-plane is 0. So we get 0 degrees. Okay, so we're going to draw that right over here, just making a little more room. And we are going to draw, so this is our S-plane. So this is the real and imaginary. Okay, so we have 1 point. So, and remember here we're thinking angle is around, so this is the angle of 0. This would be 180, goes all the way around. So our first point that we can plot for 0, s equals j 0, so essentially DC, no frequency, that would be a magnitude of 1. So we're going to put it over here. This is 1. Put a magnitude of 1 and 0 angle. So that would be this point. This is equal to, this is s equals j times 0. Okay? So that's 1 point, but there's many points we need to plot. So we're going to jump to specific points, and later you'll see how you can kind of approximate those. The next point that's going to be useful for us to plot is going to be when we actually equal exactly 1. So we're going to do, let's try s equals j times 1. So omega is equal to 1. And let's put that into here and see what we get. So we're going to look at the magnitude of 1 over, so now we're looking at j times 1, right, plus 1. And we need to do some math on that, so we need to multiply by the conjugate and change it all around. We'll find that we will get, our answer in here will be 1/2 plus, minus j times 1/2, the magnitude of that. And so that's the same as the root 2 over 2 as an output. So our magnitude would be root 2 over 2, because this is just 2 equal side lengths. So this would be our magnitude. And then our angle if we look at, actually we can draw it on here first, and sometimes it's actually easier to draw it out in the plane first to understand it. So what this would be, our answer here would be 1/2 in the real dimensions, this is 1/2, and then 1/2 negative in the imaginary. So this is, we'll put negative 1/2 here. And this would be this point, which if we look at it, we see it's even, so it's going to be 45 degrees, negative 45 degrees here, and a magnitude of √2/2. Okay, so then our angle of this value, oh gosh, this was wrong, sorry. Our angle of this, √2 minus j1/2, is equal to negative 45. Okay, so we've already plotted it here because sometimes it makes sense to just look at the real and the imaginary components, but we have a point there. And then we're going to jump to one more, and it's going to be a little bit confusing. This is probably not proper notation, but we're going to take, put in parentheses, as, I guess we'll do a as a goes to infinity. Some value here, and we want to look at as a goes to infinity. Okay, so we're going to look at how you increase the frequency to infinity, how does it change? Okay, so if we put that into our equation, it's going to look a little bit weird in terms of the math of it, but so as we go to infinity, right, so it would be 1/JA plus 1, but as a goes to infinity, it dominates, right, so this could essentially be ignored, and we get 0. So we would go to 0. Okay, so then we look at the angle, and if we look at this again, so the angle of 1/JA plus 1, we're looking as a goes to infinity, then really this would be ignored and we would get 1/J, which would, if you multiply it by j/J, we get negative j. So this is equivalent to negative j. If we look at that, that is negative 90 degrees. Okay? So we now have, so let's actually plot that point. As we go to 0, it doesn't really matter which angle it is, but it will help us as we draw our circle into here. Okay, so we have 3 points plotted. We have s equals j0. This one is s equals j1, and this is infinity. I'm going to put infinity here. And we want to connect these points, because we just took discrete points, but really it's all connected. It's a linear system, right? We're increasing our frequency linearly, so we should get a path here. And we'll find that when we actually draw out every single point, we should get a semicircle that actually looks good instead of my terrible drawing. There you go. And since we know that this came in at a negative 90, this, as we move towards it, it should come in to that point from a negative 90. So this is actually the drawing on the S-plane for the frequency response. And from here we can look at the magnitude and the angle of each point as our frequency is increasing. Okay, so it might have been a little bit hard to follow, but basic idea is if you know your value, your transfer function, you can put in these different values. So you put in j omega and you test a bunch of different points. So we're looking at different frequencies, and we're going to be able to draw that on the S-plane based on their starting points, their ending points, and the angles that they're going to follow. So you can go through and test a bunch of other points, and you'll see that they should fall on this line, and from there you can get a picture of how the frequency response will change as we change the frequency.